All right, we are now going to take a look at Unit 6B, Molecular Geometry, and this really covers about the last third or quarter of Chapter 6 from the textbook. So in the first part, we talked about the types of chemical bonding, and specifically we focused on the two main types, which are covalent bonding and ionic bonding. So now we're going to take a look a little more deeply at covalent bonding and the molecules that are formed in covalent bonding and their actual three-dimensional structure, or what is called their molecular geometry. So if we take a look at molecules, molecules have certain properties, and these molecular properties depend on two things. They depend on the type of chemical bonding, and in this case we're looking at compounds that are formed through through covalent bonding to form molecules. And the second thing is their actual geometry, their molecular geometry, which as defined is the three-dimensional arrangement of a molecule's atoms in space. Now the way that a particular molecule's atoms are arranged does affect their function and their behavior and their chemical reactivity. So this is an important thing to study when we are studying chemistry. So let's move forward here. So one thing that we can conclude is that all diatomic molecules must have linear geometry. So diatomic, remember the prefix di means two, so diatomic molecules are molecules that have two atoms. So all molecules, whoops, misspelled atoms there, sorry. All molecules that are made up of just two atoms are going to have what is called linear geometry. They'll just be in a straight line. There's a couple examples here. We have hydrogen gas, that's H2, so there's a hydrogen atom right here and a hydrogen atom right here, and they just have linear geometry, basically just a straight line from one atom to the other. Another example of a diatomic molecule is hydrogen chloride. So we have one hydrogen atom, one chlorine atom, bound together, just two atoms, so it's going to have linear geometry. And that's very simple. So whenever we see a compound or a molecule that is made up of just two atoms, we know automatically that it has to have linear geometry. There's no other option, because line is the shortest distance between 2 points. In diatomic molecules, the 2 points are the two atoms. Now, to predict the geometries of more complicated molecules, we have to consider other things. We must consider the locations of all the electron pairs that surround the bonded atoms. So all of the electron pairs, including the electron pairs that are being shared in chemical bonds, and also the electron pairs that are being unshared, that remain unshared. All of these have to be taken into account. So when we drew Lewis structures, we did have to take into account the unbonded pairs of electrons, and we had to draw them in as the little dots around the different elements in the chemical compound, but we didn't really have to do much more than that. When it comes to molecular geometry, we actually have to look at those unshared pairs and make some determinations about them, and it actually affects the geometry of the molecule. So in order to look at molecular geometry, we have a theory in chemistry called VSEPR theory. So VSEPR theory is a theory of chemical bonding that states that repulsion between the sets of valence level electrons, so the repulsion between valence electrons that surround an atom, cause these sets to be oriented as far apart as possible. So VSEPR theory, and this is logical, says that the electrons, the valence electrons that surround atoms, repel each other. And so atoms that are involved in chemical bonds are going to arrange themselves in such a way that they are as far apart as possible because their valence electrons are repelling each other. Now, VSEPR theory stands for valence shell electron pair repulsion. So this is valence shell electron pair repulsion theory. So, and it's based on the fact that like charged electrons are going to be repelling each other. So in VSEPR, we use a code to represent atoms and unshared pairs of electrons. So in VSEPR theory, there's a particular code that we use, and this code is something, there's a small amount of things you have to memorize, and this code will help you to predict the geometry of different molecules. So the first code is, we have the letter A. A is equal to the central atom. And then we have the letter B, and the letter B represents all atoms that are bound to the central atom. B are the atoms that are bound to the central atom. And then we have letter E, which represents any unshared electron pairs. Now, the unshared, it's italicized here, the unshared is crucial that you understand we're talking about electron pairs that are not part of a chemical bond. So we have three-letter code here to represent different molecules. We have A representing the central atom, B represents the atoms that are bound to the central atom, and E represents unshared electron pairs around the central atom, actually. And maybe I need to specify that. So unshared electron pairs around the central atom. All right, so for example, BeF2, beryllium difluoride. Be is an exception. Beryllium is an exception. Sorry about this. I'll restart that later. Beryllium is an exception to the octet rule, which means it is okay with just 4 valence electrons. Now, we haven't learned about any exceptions up to this point, but now we're going to learn that there are some exceptions. Basically, you'll be told that there are exceptions. These elements are exceptions to the octet rule. So if we look at beryllium difluoride or beryllium fluoride, I should say, and we look at how this is constructed, we see that when we draw a Lewis structure, we have beryllium in the center, and it's got two shared electrons there, 2 shared electrons right there. We could draw those. We could draw the Lewis structure, and actually I would recommend to draw it this way, but where I got this particular image from, did not draw them this way, but I would recommend you draw them with the lines representing the chemical bonds. Okay, so if we take a look at this, we have beryllium as our central atom, and then we have 2 fluorine atoms attached to it. Now, according to VSEPR theory, the shared electrons will be as far apart as possible. So in BeF2, beryllium fluoride, this is a straight line. BeF2 can be represented as AB2 and has a linear molecular geometry. Now, this is the key here. This code right here, AB2, you need to know how to derive that code from the molecule. So, and from the Lewis structure of the molecule. So we know that, remember, I'll scroll up just a little bit. We know that the code says that A represents the central atom, B represents atoms that are bound to the central atom, and E will represent unshared electron pairs, and this is key, I should have added it in, around the central atom. Okay. So beryllium fluoride has a code of AB2 because the beryllium is a central atom. So the beryllium is a central atom, and that is A. And then it has 2, so here's your beryllium central atom, and then it has 2 fluorines attached to it. So B are the atoms bound to the central atom, so it's AB2, and there's 2 of them. And there are no unshared pairs of electrons because these 2 electrons here and these 2 electrons are being shared. Beryllium has no other unshared pairs of electrons around it, so there is no E. So AB2 is linear molecular geometry, and this is something that you'll sort of have to memorize. But there's just a handful of these. So BF3 is another example. So boron trifluoride. Boron is also an exception to the octet rule because boron is okay with just 6 valence electrons. So boron is okay with 6 valence electrons, and BF3 can be represented as AB3. And this has a type of geometry called trigonal planar geometry. All right, so let's take a look at this. So here's a more familiar looking Lewis structure with the lines representing the covalent bonds, which I prefer personally. So we have BF3. Now we see that A represents our central atom. We always have an A for our code, and that's our boron right here. And then we have 3 fluorines attached to the boron. So there's those 3 fluorines are B's, that's their code, because they are atoms attached to the central atom, and there are 3 of them, so AB3. Now AB3 has a particular geometry called trigonal planar. Basically, it's all on one plane, and it sort of has a triangular shape to it. We're going to look at some models in class to help with this. All right, so now moving on, another example. Another example we have is CH4. So CH4 can be represented as, and let's do this first. So here's a representation of CH4 right here, a Lewis structure. And we know that carbon will be our central atom, so there's carbon. And this is called a ball and stick model. These models are called ball and stick models, and they help to show you bond angles and geometry. I'm not sure how much we'll talk about bond angles in this class right now, but we know we have carbon, and we have 4 hydrogens bound to that carbon? Well, that central carbon is going to have the letter A. We always have that central atom, that's A. And then the central carbon has 4 hydrogens bound to it, so that's the hydrogens are given the code letter B. So we have a central atom, that's A, and then we have 4 other atoms attached to it. So the code is AB4, and the carbon has no unshared pairs of electrons around it. So you see here that CH4 can be represented as AB4, and this is a different kind of geometry. This is called tetrahedral geometry. And so this particular geometry here is called tetrahedral, where we have one central atom with 4 atoms bound to it and no unshared pairs of electrons. Next example, NH3. Now, NH3 has only 3 bonded pairs of electrons, or shared pairs of electrons. Now here is our first situation where we are going to use the letter E in our code. So there's a Lewis structure for NH3. We see the total number of valence electrons are 8, and so we draw the central nitrogen atom, attach the 4 hydrogens to it, and then that takes up 6 of our 8 electrons, and then the remaining 2 have to go as an unshared pair right here around that nitrogen atom. So when we draw the code, we have to take into account that it has an unshared pair of electrons around the central atom. Okay. Which is nitrogen. All right, so let's try to see if we can derive the code here before we actually move on. So N is our central atom that gets the code letter A. It has 3 hydrogens around it. So B are the atoms attached to the central atom, and there are 3 of them. And now we see there's this unshared pair of electrons. If we go back and look at the code, the letter E, we see right here, the letter E represents the unshared electron pair. So we go down here and we see we have 1 unshared electron pair right there around the central atom. So that means, whoops, sorry, AB3, this is our nitrogen, these are our 3 hydrogens, and then we put 1 letter E right there to represent this unshared pair of electrons. So the code for this particular molecule is AB3E, and it may not be apparent yet, but these codes, we use these codes to determine the geometry. If the codes are associated with different shapes, maybe I should have said that earlier, but the code tells us what shape this particular molecule is going to be. So if we see AB3E, we know that it's going to be a specific kind of geometry. So these unshared electron pairs cannot be ignored. They occupy space and they repel other electron sets. And this picture down here actually gives kind of a good representation of this. So if we were to look at NH3, this ammonia, we see that we have the central nitrogen atom. We've got 3 hydrogens attached to it here, actual atoms, and there are these shared electrons that are in between the nitrogen and those hydrogens. But nitrogen also has this unshared pair of electrons that are real, and they occupy space, and they actually are going to repel. They're going to repel those hydrogen atoms because of their valence electrons. There's going to be this electron, these valence shell electron repulsion, and that's where this the VSEPR theory comes from, valence shell electron pair repulsion. And so those electrons that are not bound to any other atom are still going to be repelling other atoms because of their negative charge, or other electrons because of their negative charge. I'll clean this up a little bit, undo some of this. All right, so they have to be accounted for when we are looking for geometry. When we're doing a Lewis structure, we do draw them in. When we get into geometry, we actually have to account for them, and they are incorporated into the code by the letter E. So NH3 can be represented as AB3E, which we just did up here. So, and it has a particular kind of geometry that is called trigonal pyramidal. Trigonal pyramidal. Now these terms are a little difficult at first, but you kind of get the hang of them. There's not a whole lot. And I think I'll make a Quizlet study set for this. But basically, we have our nitrogen right here, and we have our 3 hydrogens. Now, at first glance, you might think that this should look like our boron trifluoride right here and have a trigonal planar geometry. But the reason that boron has a trigonal planar geometry, which actually is like a flat molecule, if you looked at it from the side, you'd see boron and then a fluorine here, and then you'd see a fluorine here, and it would be hiding the other fluorine that would be behind it back here, because it's on a plane. But boron doesn't have another unshared pair of electrons. If it had another unshared pair of electrons, it would be repelling all these other fluorines away. But it doesn't have that because boron is okay with having just 6 valence electrons. So it's an exception. Nitrogen, however, is not okay with having just 6 valence electrons. So it actually has this unshared pair of electrons here. So even though it has just 3 atoms bound to the central atom, they are repelled by this unshared pair of electrons that's hanging out on top of that nitrogen. And so it pushes away those hydrogens and it changes the shape of the molecule, and we have to account for that. All right, so this type of shape is called trigonal pyramidal, and it has a different kind of geometry and different bond angles. Another example, water. So H2O. Water has 2 bonded atoms, 2 bonded or shared, and therefore it has 2 shared pairs of electrons. So remember, if we were to do the Lewis structure of water, we see it right here. Each hydrogen has 2 valence electrons. Oxygen has 6, so there's a total of 8 valence electrons. There's 2 there. There's 2 more there for 4, and then we have 6 and 8, and that's how we draw the Lewis structure of water. But when we take a look at this and we try to code this, we see that our oxygen, that has the letter A, it's a central atom, has 2 hydrogens attached to it. So it's AB with 2 hydrogens, but now when we look at the oxygen, we see that there are 2 unshared pairs of electrons there, and so that each of those we have to count for. So we give an E for the unshared electron pairs, and there are 2 of them. So it's AB2, E2. I hope this code does not seem too complicated. We'll work on this quite a bit in class. So H2O has 2 bonded or shared pairs of electrons and 2 unshared pairs of electrons around the central atom, which is oxygen. So it has 2 bonded pairs of electrons, and here's one right there, 1 bonded pair, and there's another bonded pair. Those are the electron pairs that it's sharing with the hydrogens, and then 2 unshared pairs, which are here and here. All right, so if we coded this out, we already did it, AB2E2, but we see that water can be represented as AB2E2, and it has a different kind of geometry. The geometry of water is called bent, has a bent geometry. And if we look at this particular orbital model that we see here, we see our central oxygen atom, and we see the 2 hydrogen atoms, and remember they are sharing these valence electrons, but then the oxygen still has 2 unshared pairs of electrons out there, and they are repelling those hydrogen atoms away from them, And so if we could actually see the water molecule, we would see our central oxygen atom, and those 2 hydrogen atoms are repelled away because what we couldn't see, actually, because they're so small, there's an unshared pair of electrons up here, an unshared pair of electrons up here, and they're pushing those hydrogens away. And so the molecule actually has what we say, or what we call, a bent appearance. And that, whoops, didn't mean to do that. So it has what we call bent appearance, and that every single molecule that has this code, AB2E2, will have a bent geometry. And actually that's something maybe I should point out. If we go back up and we say, okay, every single molecule that's AB3E is going to have this trigonal pyramidal geometry. And if we go back up and we say, okay, everything that has AB4, that is equal to tetrahedral. So we can code, based on Lewis structures, we can code our molecules with this ABE language, and then we can assign them a geometry or a shape. So AB3 is always going to be trigonal planar. And then we go back up, AB2 is always going to be linear. All right? Okay. And moving on to the last page, just a little bit here, and then this will be it for your notes for the rest of this short little unit. Example, we have carbon dioxide. So carbon dioxide has 2 double bonds on the central atom. these are treated the same as single bonds for the sake of molecular geometry. So let's do the code here. So we have a central carbon atom right here. So that would get the letter A. Actually, I can write it on here. Oops. Move that over a little bit. There's our central, I should write it as a C, I'm sorry. Carbon right there. And then we have our two oxygens attached to it. And so A would be our carbon atom. We have two oxygen atoms, and it's AB2. And notice carbon dioxide, if we look over here, carbon dioxide has no unshared pairs of electrons. None there, none there, because it has 8 that are taken up in with its bonds that it has with, its two double bonds that it has with the two oxygen atoms. So its geometry is AB2, and we can see there that AB2, we've already had an AB2. If we go back up, the first one we looked at was a beryllium fluoride. AB2 is linear. So carbon dioxide, once we code it out, we see that it also has a linear geometry. So if we could see that molecule, we'd see the central carbon atom and two oxygen atoms on either side in a straight line. All right, so here in this table right here, we see all the codes. So we see our type of molecule right here. Type of molecule, we see if it is AB2, then we know that it is linear. If it's AB3, we know it's trigonal planar. AB2E, we know it's going to be bent or angular. Bent is probably more commonly used. I would stick with that. If we see AB4, we know that that is tetrahedral. We see AB3E, we know that that is trigonal pyramidal. If we see AB2E2, which is what we saw with water, we see that that is bent. Notice that there are two different scenarios where we can have a bent molecular geometry, AB2E or AB2E2. And then if we see AB5, that's another one called trigonal bipyramidal. AB6, which can occur, that's octahedral. I think for regular chemistry, I think that if you have memorized down to right here, that means that you need to know, let's see, it looks like you need to know 1, 2, 3, 4, 5, 6 codes. So you need to know that AB2 is linear, AB3 is trigonal planar, AB2E is bent, AB4 is tetrahedral, AB3E is trigonal pyramidal, and AB2E2 is also bent, just like AB2E. If you know those 6, you'll be all set. All right, that's it for this short little unit.